Woohoo! Welcome back. Today we're going to be doing another related rates problem. I know, I'm so excited. Yay, related rates. And this time it's a water tank. Yay! Okay, so let's just dive in. See what I did? Okay, a water tank has the shape of an inverted circular cone. So it's like an ice cream cone with base radius 2 meters. I mean, that would be a really big ice cream cone. And a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic, look at this, 2 cubic meters per minute. That's a lot. Find the rate at which the water level is rising when the water is 3 meters deep. So this one is this is like the epitome of the related rates problems. Basically, anytime you're putting water into anything, your brain should just go, okay, related rates time. And what you want to do is what we've done in the past. We're going to draw a picture and see if we can find a simple geometric figure that will help us model what's going on. So I'm going to start off with the fact that this is a circular cone, and it's inverted, which basically means that we've got something that looks like this. It's basically an upside down triangle. Now, in fact, the top is a circle, but I'm going to try to keep it simple by not drawing the circle at the top. You could. You are absolutely rock on if you can, right? Because it would look more like something like this. Like that, so it looks like like an ice cream cone. Like, delicious. But I'm going to draw it like a triangle because it's going to simplify the math we've got to do. Now, we know that the entire cone is 4 meters tall. Like that. Oh, you cannot see that. Yay, bathtub. You know what? Let me see if I can make this slightly smaller for this. Ooh, look at that. Ooh, I'm like Ken Burns. Okay, so it's 4 meters tall, and then it says base radius 2 meters. What the heck does that mean? Well, base radius is right here, base radius of 2 meters. That means the base of the cone, which is, it's inverted, so the base of the cone is actually the top of the cone. I know, this is mathematicians gone wild, right? So from the center to the outside, that's going to be 2 meters. Notice that makes it 4 meters across, which is kind of interesting. 4 meters deep, 4 meters across. That's pretty cool. And we're bringing water in. So I am not going to insult you and try to draw a picture of a faucet. Many math teachers would do that. I am not going to do that. I'm going to be very minimalist, which is unlike me, but I'm going to just say, you know what, let me color it in so I don't take you to Smeary Town as best as I can. You know, down below me, FizzGig is battling the ball. And at this point, I think the ball is winning. So there's some water, H2O, a couple hydrogens and an oxygen, just for funsies. And that's getting pumped into our tank. And it says that water's being pumped into the tank at a rate of 2 cubic meters per minute. This is really important to be paying attention to the units because math problems and physics problems and engineering problems all have a nasty habit of switching things up. So this is cubic meters per minute. We got to make sure everything else is in meters. These are in meters, good. And everything else is in minutes. And if anything, wavers and ends up at kilometers or, oh goodness, feet or inches, that would be a nightmare, or seconds. So you just got to make sure everything stays consistent. So we've got water coming in at a rate of 2 cubic meters per minute. And there is water in this tank already. Here we go. You do not have to color. Coloring is not part of this. But I find that coloring is nice because it keeps the other parts of my brain from getting too bored. So they actually help out instead of fighting against me. You know, they're like, oh, yay, it's coloring. And then the part of my brain doing math is like, yeah, let's color together. Okay, so water's coming in and this depth is increasing. I'm going to call a generic depth R. What do you guys think? Now, already, if I were you, I'd be like, whoa, there's a lot of letters running around. You've got an H and an O and M's and R's, and what is even happening here? Well, the R so far is the only thing that is a variable. M is meters. Remember that. So these are meters. And we're told that we're interested in what happens when it's actually 3 meters deep. That's right there. So I'll go ahead and make that blue because that's the water. So if our main goal was to go ahead and to use all the information from the word problem and get it into an image, a picture of some sort, we've done it. So I've got my diagram. I also have a hint here that I left for you, and that's the volume of a cone is 1/3 pi r cubed h, which kind of makes sense. Let's look at this. Don't worry about the 1/3. That part, it makes sense, but we're not going to explain it now. But let's look at pi r squared. What is pi r squared? Pi r squared is, that's the area of a circle. Okay, because so remember, this is actually a circle, right? And what are we doing? We're taking the circle and we're stacking a bunch of them, right? How many of them? Each of them, right? The H, so it's one circle stacked H deep. Now you're going to say, whoa, whoa, whoa. These aren't all the same circle. And I'm going to say, yes, that's where the 1/3 comes in. It turns out that when you stack a bunch of circles like this, you end up not with half of the total of them. You end up with 1/3, which kind of makes sense because we got a little bit missing over here and a little bit missing over here, because it kind of makes sense. I'm doing a terrible job of explaining it, but it is true. So it kind of does make sense. It's a little weird. One thing I want to point out is whenever you're working with diagrams of things in 3D, if it's 3D, so if it's an object in the real world, there need to be 3 dimensions, which means 3 variables. Do we have 3 here? Yes. R squared is RR times H. So those are our 3 dimensions. There's an R and an R and an H. And so you should always look for that. So when you're trying to remember the formulas, try to remember if it's in 3D, you need 3 variables somehow, some way. Okay. So I got a bunch of stuff here, and then I said, blah, 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 similar triangles. And that's the point at which a lot of people dip, because this is a lot. But let me try to convince you in another picture, because this is beautiful and I don't want to mess it up. I want to convince you that I've got 2 similar triangles. Now, what is a similar triangle? Basically, if we look at, oh my goodness, I don't have enough colors. So I'm going to call this the red triangle right here. Ooh, isn't that a gorgeous color, red? Wow. I've got a red triangle here. And since I already colored it blue over there, I'm going to color this blue. So this triangle is going to be blue, the little baby triangle. Notice that they share the tippy top. What they don't share is this bottom part that is the red part. But this is, if this is the height, this is a right angle. And since this is along the same line, this is also a right angle. And so the big red triangle is similar to the little blue triangle because they have matching angles. This is a right angle, right? Right. See what I did there? This angle, which I'm going to just mark with a single mark like that, they share it. So we know this already matches, right? Now remember that the total number of degrees in a triangle is 180. And so if this is 90 in both, and this is matching in both, then whatever this angle is has to match this angle. And we know that from the way it's constructed. See how this is a line and these are both perpendicular to the height. That means that this angle has to match this angle. It's just the way it is. So whenever you have two stacked triangles like that, you've got similar triangles. Woohoo! Nice. So in the red triangle, we know that's this whole thing, but that was where I started out with green. We know that this is 2 meters, and we know that the little guy right there is R. Remember, this is R and this is 2. So we've already got 2 meters and R. So far, so good. And then I'm going to call this H right there. But then what is the whole height of the triangle, the red triangle, the original one? And if we look over here, we go, oh, that's 4. This is 4. And so the way this works is similar triangles, we can set up ratios. So what is the ratio? Well, I can compare. I can say R compared to 2. So those are the 2 matchy-matchy parts on this, the 2 base legs like that, is equal to, over here, H compared to 4. Those are the matchy-matchy parts. So each of the matchy-matchy parts, if you take a ratio, they're equal. And in fact, if we wanted to, we don't need to, but the little hypotenuse would be matchy-matchy with the big hypotenuse. So we could set up another ratio, but we're not going to use it. So I'm not gonna put that there in the notes and have it be confusing. Okay, so I've got similar triangles. And so this tells me that the radius and the height are interacting, right? So in other words, they're interacting. We can set them equal to each other. So I can substitute one in place of the other. Not exactly, there's some numbers involved, but I can substitute one for the other with some numbers. And so the next question is, what the heck do I want to substitute? Okay, so we got this set up. We got the picture. Let's come back over here and let's say I already know the volume is 1/3 pi r squared h. Okay, so far so good. Now, I know that this is related rates, so I'm going to take the derivative with respect to time, right? Because it's how fast everything is going. So let's look at what things I know. So the two cubic meters per minute, what is that equal to? That's the water that's coming in. So that's how fast the volume of the cone is changing. Does that make sense? So that's how the volume of the cone is changing. Okay. And then I look through here and I say, if water is being pumped into the tank at a rate of 2 cubic meters per minute, so that's the change in volume. You can't see, but I'm pointing to that. Find the rate at which the water level is rising when the water is 3 meters deep. Okay, so 3 meters is the height of the water. That's the height right there. So this is going to be my H. And then the rate at which the water level is rising, Now, is that asking me for the radius, how much the radius is changing? This one? Whether it's getting bigger or smaller, or is it asking me where the height is getting taller or smaller? And I think the water level is rising right there. That asks me to know what dH dt is. And since I know what the h is at any given time, and I'm looking for the let me rephrase. I know what h is at the time when I'm interested in looking at this problem. It tells me when the water is 3 meters deep, so I know the height. And I'm interested in dH dt. That all tells me that I want to use this to eliminate r. I've got too many variables. So because in here, do I ever get told how the radius is changing? Do we talk about the radius changing at all? No. We've got one piece of information. That's the base radius. That's it. And so could we deal with the radius? Yeah, we could, because we've got Pythagorean theorem, and so we could, but that is so messy. Let's just get rid of r. Let's replace r with h. So r over 2 equals h over 4. I'm going to multiply both by 2, and I get r equals h over 2. Right? Sorry about that. So I've got r equals h over 2. Okay, I think I'm going to go on to another piece of paper. So I've got v equals 1/3 pi r squared h. So I just found out that r is h over 2. So I can square that times h. So I'm just eliminating r from the very beginning. And this is going to make it a lot more streamlined. Again, could we do it a different way? Absolutely, but that's not the way I'm going to do it. The way I'm going to do it is to eliminate h. So then I've got that the volume is 1/3 pi times h cubed over 4. Now take a good look at what I just did. Do you understand how I got from here to here? There are 2 h's times h, that's 3 of them. Now how many 2's are there? 2 squared is 4. Okay. Now, is this always true of all cones? No. This is only true of cones when the setup looks like this. A height of 4, a base radius of 2. If we had a different set of information, we'd have a different volume. So we can't assume this for all cones. This is just the cone we're working with. I got all V's and H's. I'm going to go ahead and differentiate. So let's do some implicit differentiation. I'm going to take dv dt. And then over here, remember the numbers out in front, the coefficients, as long as they're multiplied, which they are, they're just going to wait. And then I'm going to take the derivative with respect to t of h cubed over 4. Okay, so I've got dv dt. How the volume is changing with respect to time is 1/3 times pi. Okay, now we're going to have to do some fun stuff. Fun. H cubed. The cube is going to come in front, so I've got 3 times h squared. Now, keep in mind, this is all over 4. The 4 just hangs out. It's just a number. And then I have to multiply, because then I have to go to the inside and say whatever the derivative of h is with respect to t. Now, before I go and mess with this anymore, I notice that there's a 3 and a 3, and I can cancel them. So I'm going to go ahead and do that. So dv dt is pi over 4 times h squared times dh dt. So how the height is changing with respect to time. Okay, now I'm thrilled because this is what we want. We want to know how the height of the water is changing. How is the water, how fast is the water rising? And we know dv dt from the other page. That's going to be 2 cubic meters per minute. We've got pi over 4. And then I've got h squared. And h squared was, what was the height? The height was 3. And then this is going to be dh dt. Now, for those of you who are big fans of units, if you like to keep track of such things, this is cubic meters per minute. This is meters. Oops, sorry. It's meters squared. And then this is going to be meters per minute. So it's very cool because you do end up with cubic meters per minute because it's meters squared times meters per minute. And remember that these don't have units attached. They're just, they're just coefficients. So, I mean, not that they're not very important. They're very, very important. I don't want them to feel bad, but they don't carry units with them in this case. So let's see. I've got 2 equals 9 pi over 4 times dh dt. Oh, this is very exciting. Are you excited? I'm excited, but I've run out of paper. So let's go into another paper. We're almost there. We're almost there. Related rates. They take forever, but are they possible? Yes. Do I love them? Okay, so what do we want? We want this. I don't want this anymore. It's a fraction. You can go ahead and divide both sides by that fraction if you want. I don't like dividing by fractions because then I have to remember to flip everything over. So I'm going to use the method, and hopefully you guys have already started and you're not even waiting for me at this point. I'm going to multiply by the reciprocal. You're allowed to multiply both sides of an equation by anything as long as it's consistent. So I'm going to multiply both sides by 4 over 9 pi. The 4's cancel, the 9 pi's cancel. I end up with just the dh over dt. And over here, I have 8 over 9 pi is dh dt. Or the water is rising at a rate of 8 over 9 pi meters per minute. Why do I know it's meters per minute? Well, because I know it has to be, but also because I did this cute little thing where I figured this out over. Oops, sorry, you can't see. Where I figured these, so you can check the units, or you can just say, well, we know what it's going to be. It's all in meters and minutes. We did it. Yay, we did it. Oh my gosh, woohoo, yay, woohoo. So, what are the steps? Because that was a long problem. So let's review the steps. I know I'm at 23 minutes, but just let me take another 30 seconds. So you're going to read the word problem. You're going to panic or cry, go grab some support ice cream, whatever you need. And then you're going to come back and you're going to draw pictures and try to come up with shapes. It's usually going to be hopefully a circle, a triangle, a square, a rectangle, something like that. Usually there's something you can draw that we also know facts about. Now, triangle, normally we're thinking Pythagoras, but what I want to encourage you to consider is if you have stacked triangles like that, like a little one and a bigger one, those are similar triangles, and so we can set up ratios like this. So we come up with a formula, and we see what we can do with the formula. Then we have this other formula, so we actually have 2 in this case, and that was the formula that tells us about the volume. Why do we know to look at the volume? Well, in this case, the water is being pumped into the tank at a rate of 2 cubic meters per minute. Cubic meters, that's a volume. That's in 3D. So that's a volume per time. So it's dV dt. So we get this equation. And then what we did was, instead of dealing with R and H as being 2 separate variables, because that was going to be a lot, we went ahead and we converted the R into an H. And then when we took the derivative, we only had to worry about dH dt and dV dt, which make things a lot easier. We plugged in values, we solved, and we got the answer, which then we wrote in a sentence. That's pretty good. So we're done. And it's slightly under 25 minutes. Nicely done, you guys. We're so awesome. Okay, big blue star for everybody. Woohoo! And you guys need to go out, whatever time it is. Get outside. If you need to howl at the moon, howl at the moon. Howl at the sun. Howl at whatever's out there. Stars, trees, your neighbors. Well, maybe not your neighbors, but you know what I mean. So howl at something. Enjoy, but look out far because you've been staring at the screen for a long time. So you got to give your eyes a little rest. So look at something that's really far away, or even close your eyes and just think, yay, I'm so awesome. I can do related rates. We can do related rates. Yeah, dance party related rates. And then come back, get something to drink, get something to eat. Remember to eat protein. Remember to eat your vegetables. Remember to eat a little bit of fruit. You know, all the things that are good for you. And get lots of water. And maybe even something that's treat-like, you know, I know I'm thinking about ice cream cones myself right now because, you know, you could be like, hey, guys, if you got an ice cream cone that has ice cream, so it's like a sphere on top of a cone, and I'm eating at a rate of cubic centimeter per second. I'm very hungry. How fast is the height of the ice cream cone decreasing? Something like that. You could totally do it. So you could do ice cream related rates. Hey! Or not. You can just take a break and do something else. But take care of yourself. Give yourself a big hug. You did awesome. And I will see you in the very next video. Woohoo. And math on. Related rates on. Well, maybe I went too far. No, I take it back. Just math on. Woohoo.